morning put me in view of the Bible.
Works.
Maybe I see in front of that.
Oh,
See, somewhere this way or that way.
check. Yeah.
Signal. It's free. That's right. It's expensive. There is no laptop today? No.
Yeah, because it sort of depends on the page.
But it's not working. I've done something.
What happened after?
I don't know, it doesn't work. Maybe I have to reboot the computer?
Yeah.
Okay, it doesn't work.
No?
Doesn't care at all about the computer.
No? Something's...
Something happened. Hi.
So, fine.
Very thoughtful. This might take several minutes. Almost.
Okay. Stickers at the end.
Woohoo.
You know organic or open? Inorganic. What was the subject of it? Organic.
Black boards.
It's something.
Haha.
This is what? Oh, that's the year.
It's all sitting.
Yeah, I think that she's so.
They are sitting.
Yeah,
That
it's
is
from Brazil. First, $50.
How much will it cost back home?
50 real, which is $10.
So they are charging 5 times more? So 4 times more. Yeah.
So,
That's why you always ask it from back home. So if somebody's coming, just ask them to bring the dust.
Okay, let's go ahead and get started. Okay, so, oops. This is the first lecture for 5104-004. So we're changing from chemical kinetics to chemical reaction dynamics. Most of the things on the syllabus are similar to what was on the previous syllabus. So the required textbook for this course is the same as the required textbook for the kinetics course. It's this book by Houston. It's available online for about $30, I think, or if you Google it, you will find a PDF, of which I don't know whether it's legal or not, but
yeah.
thanks
to Russian brothers there. Find it.
Exactly.
We have already done illegal things.
Yeah, so I might be taking some material from some other textbooks. If you need to access those, I'll put them on the blackboard, the relevant sections. For this course, I am assuming that you've had some introduction to quantum mechanics on the graduate level. But, you know, I kind of know, you know, those of you who are in the kinetics course, you know, I kind of know what background you're on, so I can make adjustments if necessary. We are going to be doing some of the problem sets are going to involve numerical calculations, so it's good if you have access to numerical software such as MATLAB, Mathematica, Maple. Some of you are using Python, that's also okay. Yeah, and if we really need to use this, then I will also give some introduction. Okay, I think you know the university policies. Okay, so the course outline. We're going to be talking about, we're going to spend the first few weeks talking about scattering. So scattering of molecules, how they exchange energy, how they react with one another, how we learn very detailed information about chemical reaction dynamics from scattering experiments. Then we're going to be talking about potential energy surfaces. We're going to be learning about things like Polanyi rules, which tell us, you know, this is kind of the zeroth order way that we understand how the initial and final quantum states play a role in a chemical reaction. We're also going to be talking about non-adiabatic effects when more than one potential energy surface is involved. Next, we'll do a section on photochemistry, including some modern topics like roaming reactions. And finally, we're going to look at some modern research topics, including molecular reaction dynamics at surfaces and in condensed phases. Okay, the homework and problem sets and final exams, this is going to be similar to the previous course. I'm going to try to have instead of having just like 1 or 2 problem sets, I'm going to try to have 2 or 3, but keep them relatively short, and then there'll be a final exam. Okay, any questions about the syllabus? Okay. Oops. Where did this go? Do you remember which one it is? Is it this one? I don't think so. Okay, well maybe it disappeared. Okay, well never mind.
You want to download the PDF?
I just wanted to put on the screen.
Oh. This screen looks like probably one of the super controls everywhere like that. Did you get this one for school? It looks like went everywhere. And people know that he's why Franklin is the guy. Did you
Yep.
respond?
Okay. So the last homework is due today for kinetics, and I will also I will get it graded as soon as I can, hopefully by tomorrow-ish, and I will also get the final exam posted as soon as I can, hopefully by tomorrow, for kinetics.
When should we send you our homework today? By the end of the day or?
I think I said this morning, but as soon as you can.
Okay.
Okay, so we are now in chemistry 5104-004, and this is chemical reaction dynamics. Okay, so what is chemical reaction dynamics? How does this differ from kinetics? Well, kinetics describes the rate of change of concentration of species versus time, but in reaction dynamics, we want a more specific, detailed, microscopic picture. And so as you could see from our study of chemical kinetics, when we started coming up with models for describing chemical kinetics, you can see that maybe these microscopic pictures are going to be important, because we saw, for example, in transition state theory that the specific structure of the transition state of a reaction is important, right? So we need to understand, if we really want to understand what's going on, we need to know these microscopic details. Okay, so this topic is going to involve a microscopic picture of how reactions take place. Okay, and so we're going to be concerned with things like state-to-state reaction rates. So this is what we're going to start talking about today. So basically we've learned about the overall reaction rate of a particular chemical species, but what if it's in a particular quantum state versus in another particular quantum state? Okay. What about the dependence? So we started talking about this a bit in collision theory, right, with the steric factor. But what about the dependence on, if you have a molecular collision leading to a reaction, how does that depend on the orientation of the molecules, on the angle of collision, collision energy, and other parameters. Okay, what about electronic effects? And in particular, is there a Born-Oppenheimer potential energy surface for the reaction? Right, so basically a potential energy surface describing the motion of the nuclei on in a single electronic state. Or do we have non-adiabatic effects, which mean basically there's interaction between multiple different electronic states that are important for describing the reaction. Okay, and then what about, so far we've been deriving rate constants that are a function of temperature, but what if there's not a well-defined temperature? What if you have a reaction taking place under non-equilibrium conditions? And under these conditions, maybe you have basically some non-Boltzmann distribution of states that you can measure, but it doesn't correspond to a temperature. And how does that affect the rate of reaction? Okay? Okay, so right now, I'm sort of following the material from the textbook, chapter 8. We've sort of, in our kinetics course, we sort of loosely covered chapters 1 through 3 and then 5 and 6. I kind of skipped most of chapter 4, except we did talk a bit about diffusion. That's covered in chapter 4. And so now I'll cover chapter 8, then we're going to go back and cover chapter 7, and then we're going to take some material from other sources. But right now you can follow Houston chapter 8. Okay, so we're going to start, I'll just give you an example of a reaction where state-to-state reaction kinetics are, play an important role. So as an example, we can consider the simple reaction. Fluorine radical reacts with H2 to make HF plus H. And one of the reasons why physical chemists were very interested in this reaction was because they wanted to use it, and they've used it successfully, in fact, to make what's called a chemical laser. So in order for a laser to work, basically you have to have what's called a population inversion, meaning you have a situation where there's an excited state level that has more population then a lower level, right? This is called a population inversion. And when you come in with a photon that has the right wavelength, right, to stimulate either an absorption or an emission of this transition, then if you have a population inversion, it will preferentially do stimulated emission. It'll cause population to relax from the upper state to the lower state, and it'll generate more photons. Right, so this is called light amplification by stimulated emission of radiation. That's what LASER stands for. Amplification by stimulated emission of radiation. Okay. And in 1961, Palagi, Dudley Hirschbach, and Y.T. Lee won the Nobel Prize for their work on molecular beam dynamics involving reactions like this one, including this one. Okay, so I wanted to show you a figure, but the screen wasn't working, so I'll just draw it. Okay, so if you look at this reaction, the energetics look like this. So F plus D2, so it's easier experimentally to study the reaction with D2 instead of H2, so we have more detail about that. So this reaction is exothermic by about 150 kilojoules per mole. And there are 4 different vibrational levels. So this is V equals 0, V equals 1, 2, 3, 4. So actually 5 levels if you include V equals 0. So there's 5 vibrational levels that are accessible if you start with the reactants in their ground state. And you can measure the relative probability of exciting each, or of ending up with the DF product in each of these vibrational levels. And you can do that either using chemiluminescence, where you basically do the reaction and then measure the emission of light. And you can measure the wavelength at which the light is emitted, and you can tell how many molecules are in each state based on, you know, each of these transitions has a different wavelength. Or you can do a molecular beam experiment where you take molecular beams of fluorine atoms and H2 and scatter them, and then you look at the kinetic energy of the HF products. And based on energy conservation, you can tell, based on the kinetic energy, which vibrational state you ended up in. Because due to conservation of energy, if you have more internal energy, then you're going to end up with less kinetic energy, and vice versa. We'll go into detail about this later, but that's the basic idea. Okay, but the result that you get, if you look at these different vibrational states, so if you plot on the x-axis the relative probability, then basically you end up with nothing in the ground state, but you have a maximum at V equals 3, and then less V equals 4. So it looks something like that. Okay, and so this gives a population inversion because, for example, you have more population in V equals 3 than you have in V equals 2. So basically you can make a laser by, if you have two end mirrors, and then in between you have a gas cell containing F2 and H2. And then if you send an electric discharge through the gas cell, you can break apart the F2 molecules and make F radicals. Right? And then this reaction can take place, and then you end up with HF plus, H plus F. Right, so you end up with HF that preferentially gets excited to V equals 3. And then you have HF, it's excited, it starts emitting radiation at the frequency of V equals 3 to V equals 2, because this is a strongly allowed transition. And because you have a population inversion, there's spontaneous there's amplification of the stimulated emission. Okay? Any questions about that? Okay, so this kind of raises the question, how do we understand why this happens? What, features of the reaction or of the potential energy surface lead to a non-equilibrium distribution of product states? So this reaction produces a very specific non-Boltzmann distribution of product states. Does it depend on the incident state, right? So this is only what happens if you start in the ground state of the reactants. What happens if you start in excited states of the reactants? Then what distribution of product states would you get? We've talked here, this is like the overall reaction, but what if you do molecular beam experiments where you can control the relative angle of the reactants or the relative orientation, right, of the H2 molecule relative to the F molecule? How does that affect the dynamics? Right, there's all sorts of details. And then, if you know the detailed state-to-state reaction rates, how are those related to the overall reaction rate? Okay, and so that's the first thing actually that we're going to address. So we're going to look at state-to-state reaction rates. And how are those related to overall reaction rates? Okay, so if you recall, when we were talking about theories of kinetic reaction rates, we discussed collision theory. This is in chapter 3 of the Houston book, if you need a refresher, or it's in your notes if you're in the kinetic course. Okay, and we talked about the collision cross-section as a function of the relative energy of the two reactants that are undergoing a reaction. And that is defined such that what I would call the microcanonical rate constant, which just means the rate constant defined for a particular collision energy, right? Relative energy of the two species. That's equal to the relative velocity times the collision cross-section at that particular relative energy. Okay, so in collision theory, we just sort of treated molecules like they were structureless spheres, right? They didn't have any internal structure. But now we want to consider internal quantum states of the molecules, right? Vibrational states, rotational states, electronic states, and so forth. So now we can be more specific. And we can define a collision cross-section at a particular relative energy, right? Particular relative kinetic energy of the two species, and for a particular set of initial states of the reactants, and for a particular final state of the product. Okay, and that's going to be defined in an analogous way. That's going to be defined such that there's a rate constant for the reaction under the conditions where you have a particular relative kinetic energy, initial quantum state of the reactants, final quantum state of the products, and that's equal to the relative velocity times the cross-section as a function of relative kinetic energy and initial and final quantum states. Okay, so now we want to know how is the overall rate constant related to these state-specific and relative energy-specific rate constants. Okay, and so in order to answer that, we can do that in 2 steps. So if you recall from the kinetics, so the overall, so first we're going to look at the overall reaction rate. For a particular initial state. Okay, and we can make an analogy to what we've already talked about in the kinetics course, which is when you have parallel reactions. Right, which means you have a certain reactant A, it can either react to form B with rate K1, or it can react to form C with rate K2. Then if you look back in your notes, you'll recall that the rate of disappearance of A is given by the sum of the rate constants. So A, in this particular reaction mechanism, A is just going to decay exponentially, and the effective rate constant for the decay is just K1 plus K2. Okay, and we also looked at the branching ratios of products. And if you will recall, if you look back in your notes, the fraction of the products that are B products is just equal to the ratio of the K1 rate constant to the sum of the rate constants for each process. And there's an analogous expression for C. Okay, so this makes sense. If you make B faster, then you'll end up with a higher fraction of B. If you make C faster, then a higher fraction of the products will be C. Okay, and so we can use this, basically the same solutions to these differential equations to treat the problem where you have a reactant in a certain initial state, and it can react with different rate constants. So it's going to react with a rate constant for the initial state to the final state, to the first final state, we'll call it F equals 1. And then there's a different rate constant for forming the second final state from the initial state I. And so forth. Right, so this mechanism is exactly analogous to this mechanism. It's just instead of different chemical species, we're talking about different quantum states of the product, of the reaction. Does that make sense?
Mm-hmm.
Okay, so then the total rate of disappearance of the initial state I will be, we could write that as KER comma I, right, summed over all the final states. And this is going to equal to the sum of the rate constants to form each individual final state. Right, so this is going to equal to K of ER I F equals 1 plus K of relative energy I F equals 2 plus dot dot dot. Or if you want to write it in sum notation, you know, you could have many final quantum states, right? So this could be a very large series of summation. You could say it's the sum from F equals 1 to F max of K, E, R, I, F. Okay? And this F max just comes from basically energy conservation. So if you have a particular relative energy of the two reactants, and if you have a particular, initial amount of energy in the reactants, then that sort of gives you a total amount of energy that's available for the reaction, right? There might also be an exothermicity or an endothermicity that you have to take into account, but there's going to be a certain amount of energy then that's going to be available to the products, right? If we're talking about a single isolated collision, and you have to sum the final states up to the state with the highest amount of energy that's available for the reaction. Okay, we're going to do this in detail at a later time. Okay, so next, so that's how we determine the total reaction rate for a given initial state. But next we have to sum over all the initial states if we want the overall rate, right? So we're going to average right, the rate constant for each initial state over all possible initial states. Okay, and so we've talked about how to take averages. You can take an average by taking a sum or an integral. In this case, it's a sum because we have discrete quantum states from I equals 1 to infinity of the probability of having a certain initial state I times the rate. for that particular initial state I. Okay? And if we plug in our expression here for Ki, then we could also write this as, this is going to be the sum from I equals 1 to infinity of P of I times, oh, sorry, I'll write a double summation. F equals 1 to F max. Pi times K ER F. Right, so if you have a complete list of rate constants for every initial state, every final state, then you do a big double summation over all the possible, initial to final states, and this is how you would calculate the overall rate constant for a particular relative kinetic energy. Okay? Any questions? And how are you most likely, in most situations, going to calculate the probability of an initial state? Sorry? Yeah, exactly. So if you have a thermal distribution of initial states, which is not necessarily always the case, but often it's the case. So if the reactants are at thermal equilibrium, then Pi is going to depend on T. And it's going to be proportional to the degeneracy of the ith state times a Boltzmann factor involving the exponential of the energy of the ith state over kT. And to get absolute probabilities that sum to 1, you have to divide by the partition function, where Q is the sum over all of these Boltzmann factors for every state. Okay? So there's one more question that we can ask, sort of, again, looking at this analogy to the case where we had the parallel reactions involving the same reactant giving different products. So what fraction of products will be in each final state? Right, so how would, if we knew all these rates, how would we be able to derive this curve that we saw, right, where, we saw most things in V equals 3 and, fewer population in V equals 2 and so forth, right? How would we be able to calculate these populations? And the answer is we can use equations that are analogous to these ones here. So the population of a particular final state, if you have a reaction of a certain relative kinetic energy, is just going to be the rate constant leading to that final state over the sum of the rate constants summed over all the final states. Right, so if I wanted, I could put a prime here, right, to show that this is a particular f, and this is like all the f's. We're summing over every f. Okay?
Is this fraction after the reactions finish? Or,
No, it's at all times.
oh, you know.
If this is the mechanism, if it's really A goes to B and A goes to C and they're both happening simultaneously, then yeah, at all points in time during the reaction, this fraction is maintained.
Oh, okay, so.
This is assuming that there's no other processes, right? Like if you make more molecules in V equals 3 than V equals 2, like if you have spontaneous emission or something of V equals 3 to V equals 2, then you no longer are going to maintain the same fraction, right? You're going to start having more molecules in V equals 2. Or if there's collisions that deactivate V equals 3, then it's not going to be the case anymore. But assuming that this is the only process that's happening, right, is there's this one collision that causes a reaction, and then the products are isolated, they can't emit radiation.
Okay, this is dependent on time as well, or no? Did it change along the time or something?
It does not depend on time.
Oh, okay.
So the total number of products will grow with time, but the fraction of the products in a certain final state will always have this value.
Okay.
Remember when we looked at parallel reactions, basically the products look like this, where they both grow in time with the exponential that has the same k, right? It has the same exponential rate, but the asymptote is different, right? One grows asymptotically to a certain value, the other grows asymptotically to a certain value, but the ratio between these two curves is always the same.
Okay.
Okay, there's just one more thing that we need to do today, and I think we should just have time. Okay, and that is to consider the overall rate of the reaction as a function of temperature. How is that related to these microscopic rate constants for state-to-state reactions? And if you recall from collision theory, right, that's Houston chapter 3. In order to get that, we summed over, or we took an integral over the Boltzmann energy distribution. Times the rate constant for each relative energy, dE, right? So basically the probability of having a certain energy times the rate constant at that energy, right? If you do this integral, then you get the average rate constant for a particular temperature, right? Averaged over all of the relative energies. Okay, and so we can do something similar if we use our state-to-state rates. So if we have a set of rates for a particular relative energy, particular final and initial state, right? So for so if we have these kind of rate constants, then K of T is just going to equal an integral of ER goes from 0 to infinity, basically of this same thing, but now we're going to substitute the expression, how we calculated this overall rate constant at a particular energy based on summing over all the possible initial and final states. So we have this double summation of I equals 1 to infinity, and F goes from 1 to F max. And then we can take the Boltzmann energy distribution of relative kinetic energies times the probability of a certain initial state times VR times the cross-section at the particular relative energy for a particular initial and final state, and DER. Okay, does that make sense? Basically, I've just taken this expression here and substituted, instead of K of ER, I substituted basically this thing here, which is, that's the overall averaged rate constant at a particular relative kinetic energies, like averaged over, when you do the summation, this is averaged over all the initial and final states. Okay, any questions? Okay, that's all the time that we have for today. So I will see you guys on Friday, and I will send out an email when I get the homework created and when I get the final assignment posted.